In this lesson, we're going to talk about quotients of polynomial functions. A rational function is a function that can be expressed as f of x equals p of x over q of x, where p of x and q of x are both polynomial functions. So for example, 3x squared minus 1 over x plus 1 is a rational function. And 1 minus x over x squared is a rational function because in both cases we have polynomial over polynomial. But f of x equals 1 plus x over the square root of 2 minus x is not a rational function because the square root of 2 minus x is not considered a polynomial function. Now we're going to talk about point discontinuities, which are more often referred to as holes. Let's graph this function, 10x squared minus 10x plus 20 over 5x minus 10. Well, what we're going to do is we're going to factor the numerator and the denominator and simplify if possible. When we do that, we can common factor a 10 from the numerator, and then we can factor x plus 1 and x minus 2. We can factor 5 from the denominator, and we get 5 times x minus 2. And after doing our simplifying, crossing out the 10 and the 5, and then crossing out the x minus 2's, we end up with 2 times x plus 1 all over 1, or in other words, 2x plus 2. What that means is the function we were given is actually the function 2x plus 2, but so long as x doesn't equal 2. What we're going to do then is graph the line y equals 2x plus 2, but because there's a restriction stating x can't equal 2, we're going to leave a hole there. And this is what it looks like. Interesting, huh? Now, this is the line y equals 2x plus 2, but you'll see that we included a hole at the point where x equals 2. Well, it's often good to know where exactly that hole is. In other words, what's the y-coordinate of the hole? Well, we can calculate it by plugging the value of x equals 2 into the simplified version of the function. We already know that we can't plug an x value of 2 into the original version of the function because we would get 0 over 0. But we can plug an x value of 2 into the restricted portion of the function. Now that looks a little weird at first because you're saying to yourself, well, we can't plug a restricted value in, that's why it's restricted. But what we're doing is we're actually plugging that restricted value into the simplified version to determine the y-coordinate of the point that's missing. So in a weird way, it makes sense to do that. And when we do that, we let x equal 2, and y ends up equaling 6. And that tells us that the location of the hole is at the point 2, 6. All right, so to summarize, a rational function has a hole at x equals a if, reading the green portion, plugging in x equals a to the unsimplified version of f of x gives 0 over 0. But after factoring numerator and denominator and crossing out the like factors, we can plug x equals a to the simplified version, and the denominator does not equal 0 anymore. And that's what happened in our case. We ended up with 2 times x plus 1 all over 1. Well, then after simplifying, so then when we plugged in the restricted x value of 2, we got a real number. When we plugged in a 2 for x, we got a real number over a non-zero number. And that's what happened. Okay? And that's how we know we have a hole. Now, let's talk about vertical asymptotes. Imagine we're asked to graph the curve x minus 2 over x squared minus 5x plus 6. Well, we can factor the numerator and denominator and cross out like factors and state restrictions. So when we do that, we have x minus 2 over x minus 2 times x minus 3. We see that we can cross out these x minus 2's and we end up with 1 over x minus 3. But like we learned in grade 11, we are also going to state our restrictions. Well, we know if we just look at this part of the curve, that what we've basically got is the function y equals 1 over x with a d value of 3. So we're going to translate this 3 units to the right. And the horizontal asymptote will remain at y equals 0, but the vertical asymptote will move 3 units to the right and will be at x equals 3. And we also know that, though, that we have a hole from the discussion that we said earlier. Because we had x minus 2 and x minus 2, it originally made the denominator equal 0, but then we were able to cross them out and they were gone. That tells us that we have a hole at 2 comma negative 1. So in summary, we want to graph the curve y equals 1 over x, translate it 3 units to the right, and keep the horizontal asymptote where it is, and put a hole at 2, negative 1. And the curve ends up looking like this. Okay? We've got that vertical asymptote right here at x equals 3, and we've got that hole right there at the point 2 comma negative 1. But other than that, we've basically drawn the curve y equals 1 over x. So to summarize vertical asymptotes in green, we can say after factoring the numerator and denominator and crossing out like factors, x equals a makes the function f equal non-zero over 0. So what we had was 1 over x minus 3 after simplifying, like it says here, after factoring numerator and denominator and crossing out. We ended up with 1 over x minus 3. And what then happened is when we plugged in an x value of 3, we had a non-zero value over 0. And that told us that we were going to have a vertical asymptote. Okay? Now let's talk about horizontal asymptotes. We're going to consider two examples where the degree of the numerator is less than the degree of the denominator. The first one's an example we already know. The second one is new. So imagine we had the function f of x equals 1 over x. Well, we already know from grade 11 what this curve looks like. And we graph the curve and we see there's a horizontal asymptote at y equals 0. In other words, the x-axis. There's our horizontal asymptote. Well, we can also see it algebraically. Imagine we were making a table of values for the curve y equals 1 over x. As I let x get bigger and bigger and bigger and bigger, I let it get huge, we see that the y value gets closer and closer and closer to 0. So as x gets larger and larger, moving to the far right, the value of y gets closer and closer to 0, eventually getting infinitely close. It works the other way too. As the magnitude of x grows, let's look at the right-hand table of values. As the magnitude of x grows, but is negative, the value of y is getting closer and closer and closer to 0. Okay? Like it says down there. Well, what's actually happening, this is an introduction to the concept of limits. We're saying that as x approaches infinity, the limit of f of x, in other words, the y-coordinate, is 0. And we write it like this. And similarly, as x approaches negative infinity, the limit of f of x, the y-coordinate, is negative 0. As x approaches negative infinity, the limit of f of x is 0 in that direction as well. And we use that notation. And so we're going to talk about limits in depth in calculus, but for the current discussion, we can say that there's a horizontal asymptote at y equals 0. So as x goes farther and farther to the left, y gets closer and closer to 0. And as x gets farther and farther to the right, the value of y gets infinitely close to 0. Okay, so that's an example we already knew, where the degree of the numerator was less than the degree of the denominator. It was degree 0 over degree 1. But now let's talk about one where the degree of the numerator is less than the degree of the denominator, but it's actually degree 1 over degree 2 this time. Well, we can factor out the numerator and denominator and cross out the like factors and state the restrictions. Now we have 1 over x minus 3. And we actually talked about this curve a little while ago. This is basically the graph of y equals 1 over x, translated 3 units to the right with a hole at 2, negative 1. We literally graphed this one a short time ago. So what ends up happening is we get this curve, as we saw a few minutes ago. And we see that in this situation as well, the similarity we want to draw to your attention right now is that we have a horizontal asymptote at y equals 0. So in the case where we had degree 0 over degree 1, we saw we had a horizontal asymptote at y equals 0. When we had degree 1 over degree 2, we saw that we had a horizontal asymptote at y equals 0. Well, we can generalize it, and this is actually a true statement. If the degree of the numerator is less than the degree of the denominator, there will be a horizontal asymptote at y equals 0. Now, let's talk about cases where the degree of the numerator is the same as the degree of the denominator, and we'll look at two such cases. Let's do the first one here. We've got y equals 2x minus 10 over x minus 5. Well, what we can do is factor, and we end up with 2 times x minus 5 over x minus 5. We can simplify, and we can say y equals 2 so long as x doesn't equal 5. So basically what this means is graph the curve y equals 2, just a straight horizontal line with a hole where x equals 5. It looks like that. Now there's no horizontal asymptote there. There's no asymptote at all. And so what we can say is that there's not going to be a horizontal asymptote if the degree of the numerator equals the degree of the denominator, and you can cross out all the x terms in the entire expression like we did a minute ago. Okay? Now, let's talk about a situation where the degree of the numerator equals the degree of the denominator. So in both cases here, we got degree 1 over degree 1. But in this case, the x's won't cancel out. Well, in a future lesson, we're going to talk in depth about how to graph this function. But for now, let's just talk about whether or not there's a horizontal asymptote. And what we're going to do here is build a table of values and see if we can recognize a pattern. So let's let x be equal to 10, and then 100, and then 1,000, and then 10,000. When we let x have those growing values, we see that y goes from 2.14 approximately to 2.01 approximately to 2.001 approximately to 2.0001 approximately. We see that we're getting closer and closer to a y value of 2 as x gets huge. So notice that as the value of x gets larger and larger, the value of y gets closer and closer to 2. What we can say is that the limit of y as x approaches infinity is 2. And we write it this way. Now again, it's not crucial right now that you know limit notation, but that is the limit notation. And suppose that we also go the other way. We go to the far left. So we make a table of values where the magnitude of x gets larger and larger, but they're negative values. Well, the value of y, in other words, 6x plus 2 over 3x minus 1, goes from approximately 1.87 to approximately 1.99 to approximately 1.999 to approximately 1.9999. We see we're getting closer and closer to 2. So we can say that as x approaches negative infinity, goes to the far left, the value of y gets closer and closer to 2. Well, putting those two ideas together, as x goes to the far right, y is getting closer to 2. As x goes to the far left, y is getting closer to 2. Gee whiz, that means that we've got a horizontal asymptote at y equals 2. Now, what's interesting about that is we can just focus now on the lead coefficients. The lead coefficients are 6 over 3. And what does that equal? That equals 2. And that's not a coincidence. That's a general statement. When the degree of the numerator equals the degree of the denominator, and if the x terms don't all cancel out after simplifying, there's going to be a horizontal asymptote at y equals lead coefficient of numerator over lead coefficient of denominator. So now we can put all those ideas together and come up with some principles. If we have a rational expression f of x equals p of x over q of x, then one of three things is true. The degree of the numerator is greater than the degree of the denominator, in which case there's no horizontal asymptote. Okay, that would be, okay, now the next one, the degree of the numerator equals the degree of the denominator. Well, there won't be a horizontal asymptote if after factoring and simplifying the numerator and denominator are both degree 0. In other words, all the x's cancel out. Or there will be a horizontal asymptote at y as lead coefficient over lead coefficient if after factoring and simplifying the x's, some x's remain. Okay. The third scenario would be that the degree of the numerator is less than the degree of the denominator, and as we've seen, that would lead to a horizontal asymptote along the x-axis. Now, what's an oblique asymptote? If we go back a slide, we'll see that if there's the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. That's true, but there might be an oblique one. So what is that? Well, let's consider an example where the degree of the numerator is greater than the degree of the denominator, and all the x's in the denominator cancel out. Then let's consider an example where the degree of the numerator is greater than the degree of the denominator, but the x's don't all cancel out of the denominator. The first one is one we've already done before. Imagine we were to graph this function. Well, if we did that, we would common factor a 10 from the numerator and a 5 from the denominator. We'd then trinomial factor the numerator. We'd be able to cross out the 10 with the 5. And then we'd be able to cross out the x minus 2's. And we'd end up with a y value of 2x plus 2, where x doesn't equal 2. And we would see that we're going to have a hole there from our discussion earlier. And we would see again that the hole is at the point 2, 6, and we put it there. Now, the important thing to note about this curve, because we're into an oblique asymptote analysis conversation, is that there are no asymptotes. And we're going to make a general statement out of that. When the degree of the numerator is greater than the degree of the denominator and all the x terms in the denominator cancel out, there are no asymptotes. All right, let's remember that. Now let's talk about that situation where the degree of the numerator is greater than the degree of the denominator, but we can't cancel all the x's out of the denominator. Okay, let's talk about this one. We have this curve right here. Well, this numerator does not simplify. Okay, so what we're going to do is we're going to divide. That's what a fraction is. So we're going to determine the division statement. And since we can't, as it says on this slide, since we can't eliminate that x minus 2, we know that it makes the denominator equal 0, so it's either a whole or a vertical asymptote. But since there isn't an x minus 2 in the numerator to cross out with it, we see that we're going to have a vertical asymptote at x equals 2. But let's talk about the oblique asymptote. What's happening there? Well, first, we'll discuss whether or not there's a horizontal asymptote. Spoiler alert, there isn't. What we're going to do is we're going to let x have increasingly large values. So we'll let x go from 10 to 100 to 1,000 to 10,000 to 100,000. And we see that there is no one number that y is getting closer and closer to. So there's definitely no horizontal asymptote. If there was a horizontal asymptote, y would be getting closer and closer to a number. If you might recall earlier, it kept getting closer and closer to 2. Well, nothing like that's happening here. So we might think, okay, there's a vertical asymptote, but nothing else. But what we're going to do is, because I already know what the answer is going to be, we're going to put a third column on this table of values, and we are going to determine what to put in that third column. But first, we're going to do the division. We're going to divide x minus 2 into x squared minus 5x plus 5, like we did here. And we're going to come up with this expression here. Well, using our division of polynomials concepts from earlier, we're going to say, okay, f of x is equal to x minus 3 minus, and 1 over x minus 2. Well, we're going to focus just on the first part of that, just on the x minus 3 part. And we're going to let the third column actually be x minus 3, and then we're going to calculate what x minus 3 should be. So if x is 10, x minus 3 is 7. If x is 100, x minus 3 is 97. If x is 1,000, x minus 3 is 997. And we're going to continue on like that. And when we do that, when we make that column, we fill it in, we take a breath, and then we try to decide, are there any similarities? Well, look at this. 6.875 is pretty close to 7. And then 96.9898, that's even closer to 97 than the first one was to 7. And then these two numbers are even closer together than the last two numbers were. And then these two numbers are even closer together than those numbers were. And these two numbers, my God, they're so close together. It's unbelievable. So as x is getting bigger and bigger, the y value is getting closer and closer and closer to that expression of x minus 3. As x gets greater and greater, the value of y gets infinitely close to x minus 3. What that means is the line y equals x minus 3 is actually an asymptote. And since it's neither horizontal nor vertical, we call it oblique. So when the numerator is of a greater degree than the denominator and the x's in the denominator can't be canceled out, there's an oblique asymptote. So these are the asymptotes of that function. The first one is the line x equals 2. That's a vertical asymptote that we knew from our earlier analysis. The second one is the line y equals x minus 3. Grade 9 math helps us graph that. And we figured it out by getting the division statement. And this is what the curve ends up looking like. Okay. Now there are other situations where instead of looking like that, function with a vertical asymptote and an oblique asymptote, instead of looking like what's in blue, it might look like what's in red. But those will be other questions. So our summary of oblique asymptotes goes as this. If the degree of the numerator is greater than the degree of the denominator, there's an oblique asymptote and no horizontal asymptote if, after factoring and simplifying, the degree of the denominator is degree 1 or greater. There's still x's in the denominator, in other words. On the other hand, if after factoring and simplifying there are no more x terms in the denominator, then there's no oblique or horizontal. So here's a summary. When you're analyzing holes and vertical asymptotes, do it together by considering zeros of the denominator. What you do is you factor the numerator and denominator from the original expression for f of x, then simplify by crossing out like factors. If x minus a is a factor of the denominator and it's still in the denominator after you reduce by crossing out like terms, then you've got a vertical asymptote at x equals a. If x minus a is a factor of the denominator, but then it's no longer present after you reduce by crossing out like terms, then there's a hole at x equals a. And we can determine the y-coordinate of the hole by plugging an x value of a into the simplified expression of the rational function. Okay, so that's how we analyze holes and vertical asymptotes. They kind of go together in one analysis. We analyze horizontal and oblique asymptotes in another analysis, okay? What we do here is we factor the numerator and denominator and then cross out the like factors like we know how to do from earlier grades. Now, if all the terms with x have been canceled out of the denominator, there's no horizontal asymptotes or oblique asymptotes. But on the other hand, if there's still one or more terms with x in the denominator, then if the degree of the numerator is less than the degree of the denominator, you've got a horizontal asymptote at y equals 0. If the degree of the numerator equals the degree of the denominator, then you got a horizontal asymptote at y equals lead coefficient over lead coefficient. And finally, if the degree of the numerator is greater than the degree of the denominator, and there's still x's, remember, after crossing them out, then you got an oblique asymptote and no horizontal asymptote. We can determine the equation of the oblique asymptote from the first part of the division statement. And remember, so you might notice that when it comes to oblique and horizontal asymptotes, you only have one. It's either oblique or horizontal. That's all you got in this part of the course. It's possible to have, functions in later courses you might talk about, but in this part of the course, in this course, we're talking about you only have either a horizontal or an oblique, or possibly neither. With respect to holes and vertical asymptotes, though, you can have more than one. Okay? So let's do a few examples. Let's determine the equation of any asymptotes and locations of any holes for this function. Well, how would you do it? First thing you would do is factor. Then you common factor out the 2. Then you cross out these like factors of 3x minus 4, and you get this simplified expression. Now, because the 3x minus 4 has got crossed out, That means that there was a factor of 3x minus 4 in the denominator, but then after simplifying, it wasn't there anymore. That means there's a hole at x equals 4 over 3. So we're going to take that x value of 4 over 3 and plug it into what's remaining. And when we do that, we get a y value of 34 over 3. And that tells us there's a hole at 4 over 3, comma 34 over 3 in this question. There are no horizontal or oblique asymptotes because after we simplified, there were no more x's in the denominator. Okay? When we simplified, that denominator was 1. No more, no concern here for horizontal or oblique asymptotes. All right, let's try this one. We got 6x squared minus 26x plus 8 over 3x squared plus 26x minus 9. Well, what we can do is common factor out the 2 and then factor the numerator, and we get to this step here, right here. Now, we recognize that we can cancel out the 3x minus 1s, and we end up with the expression 2x minus, we can distribute the 2 in, and we end up with the expression 2x minus 8 over x plus 9. Now, we know we have a hole at an x value of 1 over 3 because when originally 3x minus 1 was a factor of the denominator, but then after we were able to cross it out. And it was gone. So that means there's a hole there. On the other hand, though, there's a vertical asymptote at x equals negative 9 because after canceling it out, the x plus 9 was still there. So we had a vertical asymptote at x equals negative 9. We got a hole at x equals 1 over 3 because of what we said earlier. We can determine the location of the hole by plugging in x equals 1 over 3 to the simplified version and determining the y value. So let's do that. Let's plug x equals 1 over 3 into the simplified version right down here. In doing that, we ultimately end up with negative 11 over 14. So we have a hole at 1 over 3, comma, negative 11 over 14. We have a vertical asymptote at x equals negative 9. After simplifying, the numerator and denominator are both degree 1. So there's still x's in the denominator. So now what we do is we look at the degrees. And because the degrees are both degree 1, we have equal degree over equal degree. That means we're going to have a horizontal asymptote at lead coefficient of numerator over lead coefficient of denominator, which is equal to 2 over 1. The coefficient up here is 2, and the coefficient down here is 1. So the horizontal asymptote is at y equals 2. Okay. Now, how about looking for asymptotes and holes for this expression right here? Well, to do this one, what we're going to do is we see we've got x plus 3 over x plus 3 times x plus 4. What we can do is cancel out the x plus 3's, and we're left with 1 over x plus 4. Well, we had an x plus 3 in the denominator, but then after simplifying, it got canceled out. So that tells me there's going to be a hole at x equals negative 3. But the x equals negative 4, while it originally made the denominator equals 0, still makes the denominator equals 0 after simplifying. That tells me I've got a vertical asymptote there. Now, in order to figure out the y-coordinate of the hole, what we're going to do is we're going to take an x value of negative 3 and plug it into here. But first, let's talk about the horizontal asymptote. The horizontal asymptote's at y equals 0 because the degree of the numerator is less than the degree of the denominator. We still have x's after simplifying. And the vertical asymptote's at x equals negative 4 as mentioned. The hole's at x equals negative 3. And the x plus 3's end up canceling out, so there's no more left. We take the x equals negative 3 and plug it into the simplified expression. When we do that, we get a y value of 1. When you take an x value of negative 3 and plug it in here, you get y equal to 1. So there's a hole at negative 3, 1. And finally, let's talk about this question. We have x squared plus 6x plus 13 over x plus 4. Well, the numerator doesn't factor, so we're not going to be able to cancel out x plus 4 in the denominator. So we've got a vertical asymptote at x equals negative 4. There are no wholes because the only value of x that made the denominator 0 was -4, and that value doesn't make the numerator equal 0. In other words, it doesn't cancel out. So we have no wholes, and we have a vertical asymptote at x equals -4. So with what's remaining, we see that we've got degree 2 over degree 1. So the degree of the numerator is greater, which means we're going to have an oblique asymptote. Well, how do we find the equation of the oblique asymptote? The division statement. We take x plus 4, and it's linear, so we can use a synthetic division. We divide that into x squared plus 6x plus 13, and we see what we come up with. Our division statement is y equals x plus 2 plus 5 over x plus 4. Well, that tells me that my oblique asymptote is this part of the division statement right there, y equals x plus 2. Okay, so hopefully that was helpful for you. It's a rather long video. Hope you enjoyed it.